Okay, so in the last class, we were looking at fields, right? Field where we can play with all the numbers, like with all the operations on the numbers, right? Addition, subtraction, multiplication, division, right? I gave you an example of field with 2 number of elements, field with 3 number of elements. And I have also shown you how to construct beautifully field with 4 number of elements, right? And I think I gave you an exercise as a T problem to construct field with 8 number of elements. How many of you are able to attack it? Very good. That's a very good thing. So actually, still I will do it because some people, still they are very confused. What is all this, right? So I'll probably do an example for field with 8 number of elements. And then again, you have a chance to construct field with 16 number of elements, right? In your assignment. So some of you might have seen that, right? And to construct the field with 16 number of elements, you need to look at a field Z2, integer modulo 2, and then take a polynomial like x raised to power 4 plus x plus 1 will work for you to build the whole system, right? You can do that as an exercise. And I think in the assignment, you will see that I have asked you to compute the square root in that field, which is tricky. How do so what is the division of, for example, 1, 0, 0, 0 divided by 1, 1, 1, 1? How do you divide these two numbers? Now, 1, 0, 0, 0 is, you can write in the power of alpha. 1, 1, 1, 1, you can write in the power of alpha. Then just simplify the power of alpha, keeping in the mind that, with respect to field with 16 number of elements, what power of alpha should be 1? 15, right? So all those calculations you can do, right? So I think you got an idea. So let me do the calculation for you for the field with 8 number of elements. After that, I'm going to show you the most beautiful mathematics, which is number theory, and how it can be applied to construct something which is very common whenever you are accessing a bank website or any secure website. So you must have come across HTTPS, how it works actually at the back end. What is the beautiful mathematics behind it, right? I'll show you the simple, that system, how it works and so on, why it is important and so on, right? So I hope that much I will be able to cover, I hope. Let us see how much I can cover. So Z2 we have done, Z3 we know. And 1 minute. I need a pen actually. So without pen, we will not be able to do anything, right? Okay, can you just check and see where is this guy? Because pen is not here, then I will not be able to do anything. Must be here on the other room, maybe. Let's check the other room. Pen. Okay, so we talked about Z2, Z3, Z4, and you know that Z4 is not a field, right? Which is fine. We know the construction from real to complex. We talked about this construction with 4 number of elements. Again, I'm just refreshing. that now here the field with 4 number of elements, just like A plus IB, we have constructed A plus alpha B. And keep in mind that there are 3 different representations for each field element. One in terms of polynomial in alpha, 0, 1, alpha, 1 plus alpha. Other one as a power of alpha, 0, 1, alpha, alpha square. And we have bits representation, 0, 0, 1, 0, 0, 1, 1, 1, right? So all these 3 representations are important. So normally when we implement these things, we can actually do implementation in the form of an array, right? So just make an array for table, right? And then you can define what is if you add this and this, what will happen and so on, and that can implement it, right? While writing the programs. Anyway, so this was a field with 4 number of elements, and we were looking at. So let me try to do calculation for this equation x cube plus x plus 1. I hope some of you have already done it, but just see what happens here. And this was for field with 9 number of elements, right? Which I'm anyway leaving for you as an exercise. So in order to construct field with 8 number of elements, so I have to look at, so because it is CF2 cube, so I look at this power 3 here, and power 3 means I'm looking at x cube plus x plus 1. And this equation has no root in the ground field. So I call alpha is the root of this equation, which is alpha cube plus alpha plus 1 is equal to 0. Alpha cube. Okay. And so we know that this is nothing but A alpha plus, sorry, A plus alpha B plus problem. A plus alpha B. Very different. It will not allow me to write anything, right? Either I have to change the way I have to write it, right? Sometime, anyway. Anyway, okay. I think there is some problem, whatever there. Anyway, so what we can do, so if we vary, so you know that there are 2 choices here, 2 choices here. C alpha square, right? Yeah. And 2 choices here, right? So basically there are 8 elements. You can write down all of them. But the easiest way is we can always compute the power of alpha, right? So what we do, so we know that elements will be 0, 1, alpha, alpha square, alpha cube. Up to this, we know everything because alpha cube is alpha plus 1. Now we compute alpha raised to power 4. So what is alpha raised to power 4 here? Alpha raised to power 4 is equal to, I think, alpha into alpha cube is equal to alpha into alpha plus 1, right? Alpha square plus alpha. Then we can compute alpha raised to power 5, which is alpha cube plus alpha square is equal to alpha plus 1 plus alpha square. Correct? Alpha raised to power 6 will be alpha square plus alpha cube, which is alpha plus 1. Alpha square plus 1. Alpha raised to power 7 is alpha cube plus alpha is equal to alpha plus 1 plus alpha is equal to 1. Right? And now you can compute the table of addition and multiplication. So I hope you can see that. Any question again here, because this is something you need to understand, right? So this is the easiest way to calculate. Just take down the power, write down the powers of alpha and express everything. So now you know that, so one representation will be in terms of power of alpha, 0, 1, alpha, alpha square, alpha cube, alpha 4, alpha 5, alpha 6. That's all. All the 8 elements will be there, right? Because alpha is for 7, again 1. Okay? That is an easy observation. And then we have these polynomial representations. So I can write down everything in terms of these polynomials of degree 2, right? So that is another representation. And then the third representation is bits 0, 0, 0, right? All these values of ABC that we have taken, right? So there are 8, right? So these 3 representations are important. It's very easy, right? So I hope you got the flavor. And 16 is something that you can play with, right? Fine. So essentially, I should summarize that there is something called tower of finite field. So we start with integer modulo 2. Then we go and build field with 4 number of elements. Then we build 2 cube, 2 cube power 4, 16, and so on. Finally, we have field 2 raised to power m elements. This is known as binary tower. Right? So, now there are different things I should tell you. In order to construct field with 4 number of elements, I have to take a degree 2 polynomial here. Right? And which should be irreducible, means no factor, no root in the ground field. And I build an GF4. Then from GF4, if I want to construct GF8, one way is take a degree 3 polynomial here and construct here. Or take some polynomial here and construct here. So this path should be for, I should leave it for your tea time. From here to here, how do we go? Display, and then you will be able to find, right? So obviously, from here to here, degree 2 is not, degree 3 is not required. From here to here, degree 3 is required, right? So how do we construct from here to here? That is I'll leave it as an exercise for you. So basically, you can build the tower. The thing is that where should I stop? From GF to raised power m, I can go a bit further. To raised power m plus 1, keep on going. So actually, there are some different things. For example, in the case of real, we know that from real to complex, right? From Q to R to C, that is a tower. And C, everything is finished. C is known as field of complex numbers is known as splitting field. Every polynomial will split completely. Or it is also known as algebraically closed field. In algebraic extension, we close. So we are not able to extend further from algebraic point of view. From this kind of approach is not working. At C, it stops. Here, so basically, you need to find, so if basically there is a algebraically closed field, so we denote it by G of 2 raised power m bar, means that is an algebraically closed field, right? So, but that's a different ball game altogether. So I don't want you to go into details, but if you are really excited about mathematics, you can actually look at some of those things, right? Otherwise, this much is enough. Now, the second thing is that this is for 2. Then we have similarly prime tower. So here we have integer modulo p, right? Then we have g of p square, g of p cube, and so on, g of p raised to power m. So q is equal to p raised to power m. So there is a field with, so if there is a field with q number of elements, q has to be a prime power. I hope you can understand. So in order to construct field with p square, you take a irreducible polynomial over zp of degree 2 to construct here, right? Same manner, everything, the method remains same, right? And you can build the whole tower. One by one, right? So this is the final way. So essentially, field with p raised power m elements, you can write down as a power of alpha. 0, 1, alpha, alpha square, and so on up to alpha raised to power p raised to power m minus 2. Got it? I'm just writing generalization. That is how you can write the whole thing. And then, so basically, if you're looking at field with periods for m elements, each element of the field can be written as a m bits. So, and those m bits you can define the operation. The most popular field is field with 256 number of elements, which is 2 raised to power 8. So there are 8 bits, which is byte. So each byte belongs to one of these field with 256 number of elements, right? So now next time somebody asks you what is byte, I mean, don't say, if you say 8 bits, people will understand this guy has a very limited knowledge, right? Byte is an element of a finite field, right? Because you can play. Unless you tell the playground, right? Don't know where we are working, right? So I hope you understand. All these ASCII values that you take, the byte string, they belong to the field with 256 number of elements, right? GF 256. Okay, any questions here? This tower is very clear. This much is enough. Later on, if required, I can talk about many other things. So normally, if you look at any algebra book, some people have asked me where to look at the material about these things, where to read. I mean, so there is a very famous book, Handbook of Finite Field, about 1200 pages. Okay, and many things are still unsolved, kind of very, very difficult, right? There are many system of equations which you will see that how do you solve? We don't have any method. Okay. By the way, as you know, Srinivas Ramanujan, once when he was very young, actually, I think this year was something around 1911 or 12. I don't remember exactly the year. He wrote a paper about solving a system of equations in one such fields. Okay. And normally, G.S. Hardy, as you know, he used to say that we never do anything useful. Whatever mathematics we have done for our own pleasure. Just like Swami Tulsidas, right? Tulsidas, if you look at Ramcharitmanas, first page he has written, Swanta Sukhai. This book I am writing for our own pleasure, right? Similarly, mathematicians do all this for their own pleasure. That is one stream. But there are other mathematicians, those who do it for the others as well, right? So, I mean, of course. So whatever is pure can be applied. So in my words, I say that if mathematics, so mathematics is mathematics. There is no pure, no applied. If you can sell it, it is applied. If you cannot sell it, it is pure. And whatever you cannot sell today, you can always sell it tomorrow, right? Because the entire business industry that you see is all at the pillar of mathematics, right? Whatever business you see, technical business or whatever, right? All the nature that you see is all full of mathematical things. For example, your tree formation. I think you should know that all these trees, if you might observe the nature, so tree at a certain angle there is a branch. That angle is fixed, right? So basically there is an algorithm working for the construction of these trees that is known as L systems. Okay, so there's a whole book, Algorithmic Botany, which you can look at it. It turns out that Steve Jobs observed these things and he created the company Pixar to create forest and animation based on those algorithms, right? So you observe something, mathematics, and then you can sell it always, right? That is what the thing. So anyway, so this is all about this finite field. Now I am going to look at certain number theoretic things. Number theory. What is number theory actually? You know what is number theory? So I think in mathematics there are 4 branches, So if you look at entire mathematics, roughly you can divide 4 main branches. One is analysis, kind of, you look at from calculus point of view. Calculus, I hope you know, right? And the other part is number theory. Another part is geometry, and then algebra. So algebra is basically, is very, very important. And I think, as you know, the discrete maths is, we study algebra actually, right? And number theory is also discrete math, right? So basically we are talking about numbers. Now, I think if you, one very important result in number theory, so basically is that any integer n greater than 1 can be written as a product of prime factors, right? Have you heard of this result? Fundamental theorem of arithmetic. If you take 15, 15 can be written as 3 into 5. 16, 2 raised to power 4, right? 18, 2 into 3 square, right? So every integer n greater than 1 can be written as a product of prime factor. This is a very fundamental theorem of arithmetic. And actually this is very, very useful also, you know. So if I want to study some algebraic structure or some mathematical structure which is discrete, so many times we look at, for example, you can see here also, we looked at the binary case which is different, Z2, GF4, ZF8 and so on. And there is a primary case, right? ZP, the prime, P square, P cube and so on, right? So basically, so if you look, so n is equal to p1 raised to power alpha 1, p2 raised to power alpha 2 and so on, pk raised to power alpha k, where pi's are primes. So these kind of this is some sort of decomposition here, right? So p1 is giving you one stream, power of p1, power of p2 is giving you another stream. So whenever we are studying a general structure on, say, integer modulo n, it is better to decompose it into different prime powers. You first study in integer modulo p1 raised to power alpha 1, and or integer modulo p2 raised to power alpha 2 and so on, and then you combine the results, you know, whenever you are trying to understand something over integer modulo n, right? And I think there are plenty of beautiful problems that one can ask, you know, in these scenarios. But anyway, so let me mention first of all some definitions about GCD. So yeah, so this is fundamental theorem of arithmetic. If n is greater than 1, n is equal to p1 raised to power alpha 1, p2 raised to power alpha 2, pk raised to power alpha k, right? This is the fundamental theorem of arithmetic. For some k primes, you know, fine. Now, if a and b are integers, a divides b if there exists an integer k such that b is equal to ak, right? Which is very normal thing, right? If b is a multiple of a, that means, you know, a divides b, right? Obviously, right? So this is something, a very basic thing. D is known as common divisor if d divides a and d divides b. If a and b are two numbers, if d divides a and d divides b, then d is known as common divisor. Then I think you must have studied these things. This is something which you already know because you are all IIT JEE or these coaching people, right? So GCD of two numbers, right, can be defined like, so if suppose I can write down a is number as p1 raised to power alpha 1, p2 raised to power alpha 2 and so on, pk raised to power alpha k, and b is equal to p1 raised to power beta 1, p2 raised to power beta 2, pk raised to power beta k. Because every number can be written as a product of prime powers, I am writing a and b as a product of prime powers. Then GCD is what? p1 raised to power, I can write down a beautiful mathematical notation. Pi, I is equal to 1 to k, minimum of alpha I comma beta I. Does it works? Right? Minimum, right? And if we take maximum, we will get LCM, right? Partial product over I, Pi maximum of alpha I beta I. Okay? And if GCD is 1, A and B are known as relatively prime. Fine. Now, there is one interesting result. If A and B are integers, then there exists integers s and t such that GCD of a and b can be written as s times a plus s times, s times a plus t times b. There exist integers s and t. So GCD of two numbers a and b can always be written as linear combination of these. So this is a simple observation. I don't have to prove anything, right? I mean, something very simple, right? You just compute the GCD. You can say that you can write down GCD as a linear combination of two. But this is a very useful fact, and we are going to use it. Okay. Hmm? Integers. Integers, yeah. So you can observe this fact, right? You just take two numbers, take the GCD, and see that you can always write down as a linear combination of integers. Fine. Another very important fact, if A divides product of B into C and GCD of A and B is 1, then A divides C. A divides B into C, GCD of A and B is 1, so obviously A will divide with C, right? It's a very simple fact to observe. Okay, so now formally, so I have told you so much about modular arithmetic, like integer modulo n and so on, but now I'm going to give the formal notation. So all the theorems and everything I differ. It's better to learn mathematics by doing examples, right? So I hope you have got hold of most of the examples, right? So now you will enjoy the definitions and so on, right? So let us see. So if n is a positive integer, z plus means positive integer, right? And a and b are integers, then we say that a is congruent to b mod n if n divides a minus b. In other words, a minus b is a multiple of n, right? Then we write down this notation. A is congruent to b mod n, right? This is the notation if n divides a minus b, or in other words, a minus b is a multiple of n. Okay, then we write a is congruent to b mod n. Means you take a divided b and looking at the remainder, whatever it is, right? Fine. So basically now what I am going to do, so in the previous examples you saw that Z2 is a field, Z3 is a field, Z4 is not a field, Z5 is field, Z6 is not a field, Z7 is a field. So essentially Zn is a field if and only if n is a prime number. So I think I told you to work over it over a cup of tea. I'm not sure how many cup of tea you've taken, but I am going to now prove it. Proof is also very, very important actually, So many times if you're not able to prove, something may work for n is equal to 10,000, 20,000, 50,000, but maybe 50,000 plus one case it will fail, right? So unless you prove it, because there are many important conjectures in number theory. For example, Goldbach conjecture. Have you heard of Goldbach conjecture? None. It is very clear that at your young age you are misguided by all these coaching people, right? Goldbach conjecture is very simple. If you can prove it, still you will get world fame. It's very simple. Any integer n greater than 4 is sum of two prime numbers. True? Looks like true. Any integer n greater than 4 is sum of two prime numbers. For example, 4 is 2 plus 2, right? 5 is right. So basically, can you prove it? Proof is still open. So if you can prove it, many times a reward of $1 million has been announced on Goldbach conjecture, right? So sorry, any even integer I am talking about, right? Any even integer greater than 4 is sum of two prime numbers. By the way, there are many such things. So basically, people try to write down computer program and try to verify. So you can verify up to the limit